Dear students, what I want to share with you is intermediate coordination numbers. My goal today is to help you understand coordination number 6. Myself, Dr. Digna Varghese. Coordination number 6. 6 coordination is the most common arrangement for metal complexes and is found in S, P, D, and F metal coordination compounds. Coordination number 6 is the most common arrangement of for metal complexes. The greatest number of 6 coordinate complexes may be derived from the octahedron that you can see in this picture. A regular octahedral arrangement obtained if the ligands are identical and its symmetry is OH symmetry. A large series of octahedral chromium 3 and cobalt 3 complexes which led Werner to formulate his theories of coordination chemistry. Okay, after this, a series of octahedral chromium and cobalt complexes, Werner formulated the theories of coordination chemistry that is known as Werner's coordination theory. Okay, and coordination number 6 means the central metal atom surrounded by 6 ligands. Okay. Geometry of coordination compounds for coordination number 6 is we know that is most common geometry is octahedral. The highly symmetrical octahedral arrangement of 6 ligands around a central metal atom and the corresponding symmetry elements of an octahedron can be shown here. In this, not all the d sigma d's are shown. Okay, so here you can see the symmetry elements. So this is the most common arrangement for coordination number 6, that is octahedral arrangement of octahedral complexes. We know for coordination number 6, the most common arrangement is octahedral, but the arrangement of ligands or the nature of ligands, which the interaction between the metal and the ligand, that will influence some distortions in octahedral complexes. Okay, the first one is tetragonal distortion. Either elongation or compression along one of the fourfold rotational axis of the octahedron. Here you can see the trans ligands, that is on the ligands at the z-axis, that is moving away from the central element, okay, or central metal atom, that can cause a distortion. So it is elongation. After elongation, there is some distortion in octahedron. So it is known as tetragonal distortion. Here you can see from this picture, the z-axis ligands are moving towards the metal ion. So here compression along one of the fourfold rotational axis of the octahedron. That can also cause tetragonal distortion from a regular octahedral geometry. So these types of elongation or compression along one of the fourfold rotational axis of octahedron can cause tetragonal distortions. This is the actual reason for the gentler effect. Second one is rhombic distortions. A trans pair of ligands are close in and another trans pair are further out can occur. Here in the same octahedron molecule, elongation and compression occurs. Okay, a trans pair of ligands can move away from the can move away, that is elongated in this direction. Okay, and one pair of ligands are close in towards the metal atom. For the same molecule, elongation or transpair out from the central metal ion or transpair ligands close in central metal ion, this can cause a rhombic distortion. Okay, Another one distortion is a trigonal antiprism or trigonal distortion. That when two opposite faces of the octahedron move away and give rise to a large family of structures that are intermediate between a regular octahedral and a trigonal prismatic geometry. Sometimes this geometry is referred to as rhombohedral geometry. Okay, here you can see two opposite faces. One is here, one is here. One is moving out and the other one is moving out but in different directions. Sorry, moving out and some other is moving out. That is always the two opposite faces of the octahedron move away and give rise to a trigonal distortion. I hope now you are clear the distortions of octahedral geometry. Once again, I will tell you the tetragonal distortion of an octahedral complex either may occur via elongation or may compression. Here you can see a perfect or regular octahedral geometry. Okay, that is of OH symmetry. If it is the trans ligands move towards the central metal ion, you can see the point, laser point at the center of the octahedron. That is, you imagine that is a metal atom. So the ligands are moving, z-axis ligands are moving closer to the central metal atom. That is forms a tetragonal distortion in an octahedral complex. Okay. The symmetry changes from OH symmetry to D4H. Okay. In the other case, there is Z out. That means the Z-axis ligands are elongated away from the metal ion. Okay, that is move away from the metal ion. So the its symmetry is changes from OH to D4H. So it is a tetragonal distortion occurs. The simplest deviation from this OH symmetry to D4H, that is tetragonal distortion, and occurs when two ligands along one axis, mainly in z-axis, differ from the other four that is given here. Okay, which are trans to each other, might be closer, okay, or than the other four, or more or away from the metal ion, or move away from the more distance from the other four ligands. It is most common for D9 configuration for copper 2 plus complex. A tetragonal distortion may occur even when all the ligands are identical because of an inherent effect known as the Jantelar distortion. Okay. Distortion of an octahedral complex that we have already seen either may occur via elongation or compression. Here you can see a regular octahedral geometry, that is after compression. Okay, this symmetry changes to D3D. After elongation, the symmetry changes to D3D. This is actually known as the trigonal distortion. A trigonal prismatic D3H complexes are rare. Here you can see a trigonal prism of D3H symmetry that is somewhat in between the trigonal antiprism and octahedral geometry. Sometimes this compound or geometry is known as rhombohedral. Okay, but found in solid, even though it is rare, but it is found in solid like molybdenum sulfide, tungsten sulfide, etc. The triangular prism is also the shape of several complexes of formula M, S2, C2, R2 thrice. The trigonal prismatic D0 complexes such as zirconium, hexamethyl zirconium, have also been isolated. Such structures require either very small sigma donor ligands bind by forming a sigma bond to the central atom or favorable ligand-ligand interactions that can constrain the complex into a trigonal prism. Such ligand-ligand interactions are often provided by ligands that contain sulfur atoms, which can form long, weak covalent bonds to each other. A chelating ligand that permits only a small bite angle, that is the angle between the metal and the ligand, can cause a distortion from octahedral towards trigonal prismatic geometry in 6 coordinate complexes. Here you can see a chelating ligand that permits only a small bite angle can distort an octahedral complex into trigonal prismatic geometry. Prism. The first example of this geometry in a discrete molecular complex was tris cis-1,2-diphenyl-ethene 1,2-dithiolatorhexene, that is ReS2C2 C6H5 twice thrice. Okay, here you can see its structure. Rhenium is the central atom and which is joined to sulfur atoms. Okay, it's a bidentate ligand in each case, that is both the sulfur atom of the thiolator compound which is attached to the central rhenium atom. Okay, here phenyl group is omitted for clarity. A significant series of trigonal prismatic complexes of ligands of the type R2C2S2. Most of these types of ligands form a trigonal prismatic geometry, was fully characterized with the rhenium, molybdenum, tungsten, vanadium, zirconium, and niobium, and suggested for other metals. Most of these types of ligands form trigonal prismatic complexes. Since the electrons involved are delocalized, here you can see the C2S2R2. Here in this particular rhenium compound, the R is phenyl group. Here phenyl group is omitted for clarity. Since the electrons are delocalized over the molecular orbitals, not only of the ligand but of the metal as well, it is impossible to assign a formal charge to the ligand or the metal. Here the addition of 2 electrons gives a negative charge. After resonance stabilization and reduction occurs and forming a thiol compound. Okay, there is a considerable ambiguity concerning the charge on this type of ligand. This is because it may be formulated either as a neutral thioketone, you can see here, or the dianion of an unsaturated dithiol. This is dithiol, the dianion of compound, and it is neutral dithioketone. The difference of 2 electrons can be represented here. Okay, so these types of ligands form complexes with the metals such as rhenium, molybdenum, tungsten, vanadium, zirconium, and niobium, and suggested for other metals also. It forms a trigonal prismatic geometry. Another configuration that is not really a distortion but involves a reduction of symmetry. It consists of the replacement of 6 unidentate ligands in a complex such as CONH3 6 3+ with a chelate rings such as ethylene diamine to form COEN thrice 3+. Okay, here you can see a unidentate ligand. In this, one nitrogen is coordinated to the metal atom. Here it is replaced by ammonia is replaced by ethylene diamine. In this, we know its molecular formula NH2CH2CH2NH2. Both the nitrogen atoms can coordinate to the metal atom. So it's a bidentate ligand and form a chelate rings. The latter complex, that means the chelated one, has no mirror plane and the symmetry of the complex has been reduced from OH to D3. Okay. For the ammonia complexes, it is OH symmetry and for COEN 3 thrice 3 plus forms its symmetry reduced from OH to D3. There is no mirror plane. The overwhelming majority of 6 coordinate complexes are octahedral, or how the shapes that are small distortions of octahedral. Okay, in octahedral complexes, there are two simple types of geometric isomerism possible for octahedral complexes. Here you can see a regular octahedral arrangement of OH symmetry. In this, the ligands are identical, that is, we can represent it as Ma6. Okay, M is the metal atom and A is the ligand. For the complexes of the type Ma2B4, here two ligands are same and other four ligands are different. Okay, that is Ma2B4 type in which the A ligands be either next to each other. You can see here from this picture, A is adjacent to one another, and in the other case A is opposite to one another. A is adjacent to one another, that is cis form. A is opposite to one another, that is trans form. So for complexes of the type Ma2B4 in which A ligands be either next to each other or in opposite apexes of the octahedron, so it can exhibit geometrical isomerism or cis-trans isomerism for octahedral complex. Complexes of this type were studied by Werner, who showed that Prisio and Vilio complexes of tetramine dichlorocobalt 3 were of this type. Okay. Two geometric isomers are also possible for complexes of the type Ma3B3. Here you can see the ligands of one type may form an equilateral. Ligands of one type may form an equilateral triangle. You can see here in the case of Ma3B3, 3A ligands and 3B ligands. Okay, that means 3 of the ligands are same and other 3 are same. Here you can see the both 3A are in the same side and here also both B are in the same side. That means that it forms a one type of equilateral triangle on one of the faces, that is the facial isomer. It is abbreviated as FAC in the name, or they may span. Okay, here in the other case, here you can see both A atoms are adjacent positions and here both B atoms are adjacent, but one B is just opposite to other. Here one A is just opposite to other. Here you can see a equilateral triangle can form in this way, that is the three positions such that two are opposite or trans to each other. Such isomer is known as meridional isomer, abbreviated as MER isomer, MER, in the name. Okay, so Ma2B4 of octahedral complex and Ma3B3 of octahedral complex can form geometrical isomerism. You can see then examples of cis and trans isomerism that we are already discussed. Once again, I will tell you the cis tritetramine dichlorocobalt 3, that is Ma2B4 type. This is Werner's Vilio complex, and trans, these two chlorine atoms are opposite side. It is Werner's Prisio complex. That is, here you can see the tetramine dichlorocobalt cis form and trans form. Examples of facial and meridional octahedral isomers of the type Ma3B3 type. Here A3 is Cl3 and B3 is H2O thrice. Here you can see the facial arrangement. Here both the three ligands are in the same plane. Here you can see the meridional isomer. This is the cis form and the meridional isomer is the trans form. Here the ligands are in opposite side. You can see in fake isomerism or isomer, any two identical ligands are adjacent or cis to each other. If these three ligands and the metal ion are in one plane, the isomer is said to be meridional or MER. A MER isomer can be considered as a combination of cis and trans. Okay, cis and trans, since it contains both trans and cis pairs of identical ligands. Here you can see both the if the ligands are in the same plane, okay, like this one, that is facial isomer. If the ligands, the three ligands and metal atoms are in one plane, that is mer isomer. Now you are, I hope you are clear. In contrast to cis-trans isomers of Ma2B4, which in which case the hundreds of isomers can be possible, for fewer Ma3B3 facial meridional isomers have been characterized. Here you can see such type RuH2 thrice Cl3, platinum NH3 thrice Br3 plus PTNH3 thrice I3 3 plus iridium H2O thrice Cl3, rhodium CH3CN3Cl3. Here you can see the cobalt complex of amine and nitro group complexes. Here metal carbonyl phosphine complex. The metal can be chromium, molybdenum, tungsten. These types of complexes can exhibit facial meridional isomerism. Optical isomerism in octahedral complexes. Trischelate complexes of the type COEN thrice 3 plus lack an improper axis of rotation. As a result, such complexes can exist in either of two enantiomeric forms or a racemic mixture of two. When we can place COEN thrice 3 plus here, it's a mirror plane, a superimposable mirror image can obtain. So it is a shows optical activity. So if we will get two enantiomeric forms or a racemic mixture of two. COEN thrice 3 plus the regular octahedral geometry, OH is the symmetry. Here the symmetry is reduced to D3. That means the lack of an improper axis of rotation. Complex ion COEN thrice 3 plus and CrOx thrice 3 minus, each of which is chiral with D3 symmetry. Here you can see the COEN thrice 3 plus complex structure, and here you can see the oxalate chromium complex. The cation dichlorobis ethylene diamine cobalt 3 exists as two geometric isomers, that is cis isomer and trans isomer. The cis isomer has a C2 symmetry and is chiral. Since the two chloride ions replace two nitrogen atoms from an ethylene diamine ring without disturbing the remaining geometry. Here you can see that ethylene diamine. In the case of COEN thrice, here also ethylene diamine present, but this ethylene diamine is replaced by two chlorine atoms, and it exists as cis form and trans form. Cis isomer has a C2 symmetry and is chiral. So the two chloride ions replace two nitrogen atoms from an ethylene diamine ring without disturbing remaining geometry. The optical activity is preserved. Okay. So cis isomer is optically active. This is an optical isomer of cis dichlorobis ethylene diamine cobalt 3 ion that is obtained from the Violio salt. The trans isomer has approximate D2H symmetry. In this case, two chlorine atoms are present in the axial positions of octahedron, that is in the Z axis. That is, the two chlorine atoms are on opposite sides. So it is a trans isomer. It possesses a D2H symmetry. So because it has a three internal mirror planes, so it is a chiral. So trans isomer is optically inactive. Trans dichlorobis ethylene diamine cobalt 2, that is derived from the Prism salt, showing one internal plane of symmetry. So it is optically inactive. Further replacement of chelate rings by paired unidentate ligands can take place as in cis, CONH3 twice, H2O twice, CN twice plus, which is chiral. Okay. But in ordinary practice, the resolution of enantiomers is limited to complexes containing chelate rings. Okay. The chelate rings provide the complex with additional stability that we know as chelate effect. In addition to the non-chelate complexes are difficult to synthesize, and it is also difficult to separate a large number of geometric isomers. In the case of this is a non-chelate compound and it is chiral and it is optically active. But we know there is a large number of geometric isomers is possible. Here we can see cis isomer is optically active. Its trans isomer, the optical activities may be different or inactive. Okay, so non-chelate complexes are difficult to synthesize because it's a separation from the large number of geometric isomers in the same port can be difficult. Okay, it is a tedious job. But in ordinary practice, the resolution of enantiomers is limited to complexes containing chelate rings. Werner synthesized and resolved optical isomers are strong corroborative evidence for his theory of octahedral coordination. It is interesting to note that in all the work since Werner, only one other completely carbon-free complex has been resolved. That is the sodium cis diaqua bis sulfamido 3, chiefly because of the difficulty of preparing non-carbon chelating agents. Here you can see the optical active enantiomer of the cis diaqua bis sulfamido 3 anion. Okay, he always done his work with carbon chelating complex. Okay, only one chelating non-carbon compound with this particular complex. One enantiomer of the tris tetramine mu dihydroxycobalt 3 cobalt 3 cation. Okay, here you can see the enantiomer of tris tetraamine mu dihydroxycobalt. Here a mu dihydroxycobalt, that means it cobalt is with the bridging hydroxyl group is here, that is represented by mu. So it's an optically active compound. To sum up the isomers of octahedral complexes, here you can see a table type examples and isomers. Here in this particular octahedral compound, if the ligands are same, it is represented as A. If it is different, it is represented by different letters like B or C or D, etc. Here, the first type is Ma6, that means the same type of ligand. It does not show any geometrical isomerism or cis-trans isomerism. If it is Ma5b, one ligand is different, or MaB5, that case there is no geometrical isomerism possible. Next one is Ma4bc or Ma4b2. In this case, the one or two ligands are different from the four ligands. Okay, here you can see in examples chromium, tetramine, dichlorido complex. The cis form is violet, whereas trans form is green in color. Cis form is here. Here the two chlorine atoms are same side. Two chlorine atoms are in the opposite side, that is trans. That is in green color. Next one is Ma3b3. That is, we know RuCl3H2O thrice, RHPy3Cl3, CONH3 thrice, NO2 thrice. In this case, we know mer isomer and facial isomer is possible. If the mer isomer means the three ligands and the metal atom in one plane, that is mer isomer. Or if it is the ligands, two of the ligands are in opposite side, that is also mer isomer. If the three ligands making an equilateral triangle, that is facial isomer. Next case is MAA2B2. Here A means bidentate ligand with the same ligand attached to the metal atom or similar ligand atom from the ligand attached to the metal atom. In the case of ethylene thiamine, both the nitrogen atoms are attached to the metal atom. Example is COEN twice Cl2 plus. Cis trans isomerism is possible. Here you can see the MAB3 type of isomer, that is CRGLY thrice. MAB3 means, and here nitrogen and oxygen is coordinated to the metal atom. This is its cis isomer and this is trans isomer. Okay. And here in this table MABCDEF, the 6 ligands are different: platinum, bromine, chloride, nitro, pyridine, ammonia. This shows 15 different geometrical isomers. Only 3 isomers could be isolated. Another one is Ma2B2C2. 5 different geometrical isomers are possible. Next one is optical isomerism from form non-superimposable mirror images. MAA3 types, that is COEN thrice. Here you can see it is optically active. And this is MAA2B2 type and MAA2BZ type. Here example is RHEN twice Cl2. Cis form is only optically active and 3 isomers is possible. Thank you for your attention.